Everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering our last and final objective for Chapter 4. In this objective, we're going to cover three main topics. First, we're going to discuss ions. Second, we're going to cover rules for nomenclature. And then third, we're going to briefly mention electrolytes. Let's start our conversation discussing ions first. When we think about ordinary chemical reactions, it's important to note that the nucleus of an atom remains unchanged. Instead, the focus is on the electrons, which can change in number during reactions. And so, the movement of electrons is fundamental. Electrons are responsible for the formation and breaking of chemical bonds, and thus they constitute the core of most chemical reactions. With that being said, it's important to pay close attention to whether a particle is a charged ion or a neutral atom. An ion has properties that differ significantly from those of a neutral molecule. An ion is a charged particle formed when the number of protons in an atom does not equal the number of electrons. And there are two types that we're going to discuss: cations and anions. A cation is a positively charged ion, which occurs when an atom has more protons than electrons. This happens because the atom loses electrons, resulting in a positive charge. On the other hand, an anion is a negatively charged ion formed when the atom has more electrons than protons. Anions gain electrons, leading to a negative charge. Now, as we delve deeper into the study of chemistry, it's essential to understand not just how substances react, but also how to identify and name them correctly. This brings us to the topic of nomenclature, which is the systematic method of naming chemical compounds. Proper nomenclature allows chemists to communicate clearly about specific compounds. Now today, we're going to specify the most important rules for naming compounds other than organic compounds. We're going to cover organic compound nomenclature in organic chemistry. We're going to begin with the systems for naming inorganic binary compounds. Now, when you're looking at a binary compound, we can determine its nature based on the types of elements involved. If both elements are nonmetals, then the compound is molecular. Some examples include water, sulfur dioxide, hydrogen chloride, or hydrochloric acid. Now, if one element is a metal and the other is a nonmetal, the compound is ionic. Examples include sodium chloride, potassium bromide, copper 2 sulfide. Now, before we actually dive into all the rules we're going to cover, it's essential to first familiarize ourselves with common monatomic cations and anions because they are going to frequently appear in various compounds. Here we see our common cations. We have hydrogen, lithium, sodium, potassium, cesium, beryllium, magnesium, calcium, barium, aluminum, and silver. And please make note of the charges that are associated with each of these cations. Then on the other side, we have our anions. We have hydride, fluoride, chloride, bromide, iodide, oxide, sulfide, nitride, and phosphide. Again, please make sure you note the charges that are associated with each of these anions. Now, with this introduction, we can begin with our different rules. And our first category is binary ionic compounds type 1. Ionic compounds, they contain a positive ion, a cation, always written first in the formula, followed by a negative ion, the anion. In naming these compounds, the following rules apply. Rule number 1, the cation is always named first and the anion second. Rule number 2, a monatomic cation takes its name from the name of the element. For example, sodium Na+ is always called sodium in the names of compounds containing this ion. Rule number 3, a monatomic anion, this is named by taking the root of the element name and then adding IDE. And so if you have Cl-, this is called chloride. This is where remembering the monatomic cations and anions from our table becomes super important. Now we can see a couple of examples here. This first compound, NaCl, our first atom is our cation, sodium. We keep its name as is. Then we have here Cl. This is chlorine. It's the anion. It's named second. And what we do is we take the root of the element name and then we add IDE. And so this is called chloride. And the name of this compound is sodium chloride. Let's do another example. Let's do this one right here. The cation is potassium. We keep that name as is. And then the anion here, we have iodine. We take the root of the element name. We add IDE, iodide. The name of this compound is potassium iodide. And you see that the same rules are applied for all of these compounds here and their names. Let's go ahead and jump into a couple of practice problems. Here we want to name each binary compound. Let's start with A. Let's look at our cation first. What do we have here? This is cesium. Now for cation, we keep the name as is. What about our anion? So this is F, this is fluorine. We keep the root of the element name and then we add IDE. So this is fluoride. And the name of this compound is cesium fluoride. Let's do the same for B. All right, what do we have here for the cation? We have aluminum. We keep that as is. We do not change it. Aluminum. What about our anion? Cl is chlorine. We keep the root of the element name and then we add IDE. This is chloride. And the name of this compound is aluminum chloride. Our last example, we have lithium for our cation. And then we have hydrogen for our anion. Now this was in our table of common monatomic cations and anions. H minus, this is hydride. You can still use the rule if you forget that, right? Hydrogen, keep the root of the element name and then add IDE, hydride. So the name of this compound is lithium hydride. Now so far, we've started with the chemical formula of a compound and decided its systematic name. The reverse process is also important. For example, if we're given the name calcium hydroxide, we can write the formula as CaOH2 because we know that calcium forms 2 plus ions and hydroxide is OH minus. We know that this is a neutral compound, and for us to ensure that, we can just swap charges to make sure we know how much of each atom we need. And so there we get it. Calcium hydroxide, CaOH2. You can also think about it as this. Calcium has a 2 plus charge. Hydroxide has a -1 charge. To make sure that you have a neutral compound, you're going to need 2 hydroxide ions to compensate for the 2 plus charge on calcium. Let's do a couple of problems to ensure we understand this. Write the formula for each compound. A says potassium iodide. Potassium, that's K plus. Iodide is I minus. All right, we swap the charges to make sure we know how much of each atom we have. Potassium iodide is Ki. Let's do the next one, gallium bromide. Gallium has a charge of 3 plus. Bromide has a charge of -1. Now we're going to swap-a-roo the charges. We get GaBr3. We're going to need 3 bromide ions to help compensate for the 3 plus charge from gallium to give us our neutral compound of gallium bromide. Now we can move into our second category, binary ionic compounds type 2. In the binary ionic compounds we just considered, type 1, the metal that's present forms only a single type of cation. That is, sodium only forms sodium plus 1. Calcium only forms calcium 2 plus, and so on. However, as we're going to see in this section, there are many metals that form more than one type of positive ion, and thus form more than one type of ionic compound with a given anion. So for example, FeCl2, it contains the iron 2 plus ion. But then if we look at FeCl3, it contains the iron 3 plus ion. The systematic names for each of these 2 iron compounds are iron 2 chloride and iron 3 chloride. What do you notice here? We used Roman numerals to indicate the charge of the iron. And so Roman numerals here are going to indicate the charge of the cation. Now, elements that form only one cation, they do not need to be identified by a Roman numeral. Common metals that do not require Roman numerals are group 1 elements, which form +1 ions, group 2 elements, which form +2 ions, and aluminum, which forms 3+ ion. In addition, something else that's important for us to mention, really quickly, let's focus on silver. This is worth making a special mention. In virtually all its compounds, silver is found as Ag+1. Therefore, although silver is a transition metal, and it can potentially form ions other than silver +1, silver compounds are usually named without a Roman numeral. So if you see AgCl, this is typically called silver chloride rather than silver 1 chloride, although the latter name is technically correct as well. Also, Roman numeral is not used with zinc compounds since zinc only forms zinc 2+ ions. Now, something else worth mentioning, I'm going to scroll back up here. Another system for naming these ionic compounds that is seen in the older literature was used for metals that form only 2 ions. The ion with the higher charge has a name ending in IC, and then the one with a lower charge has a name ending in OUS. So, a couple of ones that we need to know for the MCAT is iron. Fe3+, we can say that this is iron 3, but another name that's associated with this is ferric ion. That's the Fe3+ ion. What about the Fe2+ ion? This also has another name, ferrous ion. We need to know the systematic name as well as the old given name for iron. Also for copper. So Cu2+, this is cupric ion. Cu+1 is cuprous. These are names that we should know for these 4. Now, with that out of the way, let's go ahead and ensure we understand this by tackling a couple of practice problems. This first one wants us to give the systematic name. Okay, what do we have here for A? CuCl. Okay, when we have these kinds of type 2 compounds, the best place to start if we're trying to figure out the systematic name is looking at the anion first. Our anion is chloride. It has a -1 charge. Now, in our neutral compound, we have 1 copper atom, 1 chloride atom. So that means that the cation must be copper +1, because then when they switch their charges here, you get CuCl, which is what we're given. And that means that systematic name for this is copper 1 chloride. Wonderful. Let's tackle the next one here. We have HgO. All right, O here, because the anion is O2-, all right, this is oxide. The cation, what does it have to be to ensure that we get HgO? It's going to have to also be 2+. That way, when we swap charges, we get Hg2O2, which simplifies to HgO for ionic compounds. Now we can write out the systematic name. It's going to be mercury 2 oxide. So that's the systematic name for B. What about C? This should be written as Fe2O3. Let me correct that. We have iron, and again, we have our O2 ions, our oxide. So let's write this O2-. How many of these do we have? We have 3 of them. That gives us a total of a -6 charge. We should keep that in mind because we also know we have 2 iron atoms. What do their charge have to be to result in a neutral compound? The charge for iron is going to have to be +3 because 2 irons with +3 charge give us a total of +6 charge, which cancels out with the -6 charge to give us a neutral compound. And so then, the name for this compound is iron 3 oxide. Wonderful. Let's move into this next one. This next one says write the formula for each compound. So we're given manganese oxide, manganese 4 oxide. So this is really important. Let's write that down. We know what the charge for our cation is. It's manganese 4 plus. We have oxide. Oxide is 2 minus charge. All right, what do we need to make sure that this is balanced in terms of charge? We're going to need 2 oxide ions to get us a total charge of -4, and then that +4 and -4 cancel out appropriately to give us our neutral compound of manganese 4 oxide. And so we can write it as such, manganese O2. Beautiful. What about the next one? Lead 2 chloride. Lead 2 chloride. So lead has a charge of 2 plus, that's what's given to us. Now we know chloride usually has a -1 charge. How many chlorides are we going to need to make sure that the charge is balanced? We're going to need 2 of them. And so our compound is PbCl2. That's the formula for this compound. All right, and with that, we have covered our examples for binary compounds type 2. The next thing that we're going to move into is polyatomic ions. You came across this compound, NH4NO3. This is called ammonium nitrate, and it contains the polyatomic ions ammonium and nitrate. And you would only be able to name this if you knew the assigned special names for these polyatomic ions. Therefore, polyatomic ions, they're assigned special names that we must memorize to be able to name the compounds containing them. The most important polyatomic ions and their names are listed in this table right here. I highly recommend memorizing these. They will make your life so much easier. I'm going to go over a couple of them quickly, not the whole table, although commit the whole table to memory. I'm just going to point out a few things I want you to definitely know. The first 2 are these right here, NO2 minus and NO3 minus. This is nitrite and nitrate. Now here, I want to make an important point. Many polyatomic anions, they contain oxygen and are therefore called oxyanions. When an element forms 2 oxyanions, the name of the one with less oxygen ends in ITE, and the one with more oxygen ends in ATE. And that's what we see here. NO2 minus is nitrite, it ends in ITE, because it has less oxygens than NO3 minus, which is nitrate, ends in ATE. Another example are these next 2 as well, SO3 2 minus and SO4 2 minus. That first one is called sulfite with ITE, and SO4 2 minus is called sulfate with an ATE. Another important one to note that we just talked about is hydroxide. This is OH minus, and cyanide, CN minus. Also, please know carbonate, CO3 2 minus. And then the last thing I want to point out are these 4 right here. In an extended series of oxyanions, prefixes are also used. So here we see ClO minus. This is called hypochlorite. Then ClO2 minus, this is called chlorite. Then ClO3 minus, this is chlorate. And then ClO4 minus is perchlorate. So these are really important to know. Now the rest of these right here, these are all going to be important in both general chemistry, and we're going to see them again in organic chemistry. So might as well commit them to memory now while you're studying for general chemistry. Okay, with that out of the way, the best way to learn our polyatomic ions is to do problems. So that's exactly what we're jumping into next. The first example asks us to give the systematic name. A is Na2SO4. Now, our cation is sodium, and we keep it as such. We don't change that. Our anion is SO4, and it's specifically SO4 2 minus. We know sodium is +1, and then they swapped charges, hence why the chemical formula is Na2SO4. SO4 2 minus, this is sulfate. So the name of this compound is sodium sulfate. Okay, what about this next one? KH2PO4. We have potassium, that's our cation. So we write that down. And then our polyatomic anion, H2PO4, this is called dihydrogen phosphate. So the name of this is potassium dihydrogen phosphate. This was on our table as well. The last one we have iron, Fe, NO3, and we have 3 of these anions. Now this is important because NO3 has a charge of -1, and if we need 3 of these to create a neutral compound with Fe, then that means Fe has a +3 charge. And that's important because we're naming this compound. We need to identify the charge associated with iron. And so the name of this compound is iron 3 nitrate. Beautiful. Now this next example says write the formula for each. A says sodium hydrogen carbonate. Sodium is Na+, hydrogen carbonate is HCO3-. We do a little swapperoo with the charges, and our chemical formula for sodium hydrogen carbonate is HCO3. There we have it. All right, our last one, cesium perchlorate. Cesium is +1 charge. Perchlorate is ClO4-1. We do a swapperoo of the charges. The chemical formula for cesium perchlorate is CsClO4. And there we have it. We've completed our example problems for polyatomic ions. Again, let me reiterate, that table is really important. Please get familiar with that table. All right, next up is binary compounds type 3. Binary covalent compounds are formed between 2 nonmetals, and although these compounds do not contain ions, they're named very similarly to binary ionic compounds. In the naming of binary covalent compounds, the following rules apply. Rule number 1, the first element in the formula is named first, using the full element name. The second rule is that the second element is named as if it were an anion. Third, prefixes are used to denote the number of atoms present. And here I have a table of the prefixes. So for 1, that's mono. For 2, it's di. For 3, it's tri. 4 is tetra. 5 is penta, so on and so forth. And then our last and final rule is that the prefix mono is never used for naming the first element. So for example, if you're trying to name CO, this is called carbon monoxide, not monocarbon monoxide. So let's take a look at a couple of examples. Here we have N2O. Our first element is named first. This is just going to have the element name, so nitrogen. We have 2 nitrogen, so we're going to add the prefix di, dinitrogen. That's the first half. Then we have oxygen. We're going to name that as if it were an anion, so oxide. How many oxygens? There's 1, so monooxide. The name of this compound is dinitrogen monoxide. All right, let's look at another one. How about this next one, NO? We have nitrogen, just 1 of them. Now, nitrogen is the first element here. We're going to use the full element name, and there's 1, but because it's the first element, we're not adding mono. That's rule number 4. Prefix mono is never used for naming the first element. And then the second element is oxygen. We're going to name it as if it was an anion, oxide. And then there's only 1, so monoxide. The name for NO is nitrogen monoxide. All right, let's move on to the third one, NO2. All right, again, we start with nitrogen. There's only 1, so just nitrogen. And then we have oxygen. We have 2 of them. So the name for this compound is nitrogen dioxide. For N2O3, it's dinitrogen trioxide. For N2O4, it's dinitrogen tetroxide. Wonderful. Now, we covered a lot of rules here for naming, so let's kind of just put everything together. The first question you want to ask yourself when you're trying to work through what rules to use to name a compound is, well, is it a binary compound? If the answer is no, then the follow-up question to that is, well, are polyatomic ions present? If the answer is yes, then you want to name the compound using procedures similar to the binary compounds and referencing the polyatomic ions that you've memorized their names. All right. Now, if the answer to that is no, there are no polyatomic ions present, we haven't covered those rules just yet. We cover those in organic chemistry. Now, if your answer to the first question, is this a binary compound, is yes, then you have to follow up. Is there a metal present? If the answer to that is no, there's no metal present in our binary compound, then you want to follow the rules for binary compounds type 3. This is for binary covalent compounds. Follow the rules for that. If the answer is yes, a metal is present, you have another question you have to answer. Does the metal form more than one cation? If the answer is no, follow your rules for type 1. And if the answer is yes, follow your rules for type 2. With that, let's go ahead and tackle a couple of mixed example problems. For this first example, we want to give the systematic name. A is P4O10. So what we have here is a binary compound, but there's no metals present. So this is going to follow the rules of binary covalent compounds type 3 when we're trying to name it. Let's look at our first atom. We have phosphorus here, and we have 4 of them. So this is going to be tetraphosphorus. Now our second element is oxygen. And here we want to name it as if it were an anion, so oxide, and we have 10 of them, so decaoxide. The name for this compound is tetraphosphorus decaoxide. Then we have Nb2O5. Niobium is what that first atom is, and then we have oxygen. Now, this is a binary compound, and we have a metal present, and this metal is a transition metal, so it can have different cation forms. So we're going to follow type 2 binary compound nomenclature for this. Let's write this down. What we have is Nb. We don't know what the charge is, but we have oxygen. All right, O2 minus. Let's figure this out. We have 5 of these oxygen atoms. 5 times 2 minus, we have a total of minus 10 charge. If we're trying to compensate for it in terms of our cation charge to make sure that we get a neutral compound, what is the charge for niobium going to be if we have 2 of them? Well, it's going to be plus 5 for each to give us a plus 10 charge that perfectly cancels out with our minus 10 charge. And so then our name for this is going to be niobium 5 oxide. Simple. All right, what about our last example here, Li2O2? So here we have a binary compound. Now, is there metal present? Yes, it's lithium. Lithium only has 1 charge, lithium plus 1. So we're going to follow our type 1 binary compound nomenclature. Lithium has a charge of plus 1, and then here what we have is peroxide, O2. O2 has a 2 minus charge. Now, if that's the case, we crisscross the charges, we get Li2O2. So then we can easily name this. I just wanted to show you that that's the case. This is lithium peroxide. Wonderful. Let's move on to the second example. Write the formula for each. A is vanadium 5 fluoride. So that means vanadium has a plus 5 charge. Fluoride has a minus 1 charge. We crisscross the charges and we get VF5. That is the formula for vanadium 5 fluoride. What about dioxygen difluoride? So this prefix really helps us here. The prefix di indicates 2 of each atom. So what we have here is O2F2. That's the chemical formula for dioxygen difluoride. All right, what about for C, rubidium peroxide? So rubidium is in group 1. It has a plus 1 charge, and that's the only ion that it can form. All right, and then we have O2. This is peroxide. So this is a binary compound with a metal, and this metal can only form 1 cation. So this is a type 1 binary compound. So how we're going to name this? Well, how are we going to figure out the chemical formula? We're going to write rubidium, Rb, has a plus 1 charge. Peroxide is O2 with a 2 minus charge. We're going to crisscross these charges, and what we get is Rb2O2. So that's the chemical formula for rubidium peroxide. Wonderful. Now we want to cover one last thing, and that is how we're going to name acids. dissolved in water, certain molecules produce a solution containing free hydrogen ions or protons. These substances, acids, are going to be discussed in detail in later chapters, but we're still going to learn how to name them now. An acid, it can be viewed as a molecule with one or more hydrogen ions attached to an anion. The rules for naming acids depends on whether the anion contains oxygen. If the anion does not contain oxygen, then the acid is named with the prefix hydro and the suffix ic. For example, if we look at HCl, this acid doesn't have any oxygen, and what it's called is hydrochloric acid. All right, so it starts with the prefix hydro, ends with the suffix ic. All right, what about when the anion does contain oxygen? Then the acidic name is formed from the root name of the anion with a suffix of either ic or ous, depending on the name of the anion. If the anion name ends in ate, the suffix ic is used to the root name. So for example, if we look at H2SO4, this contains the sulfate anion, and so it's called sulfuric acid, Ic. Notice that. All right, if the anion, though, has an ending in ite, then the ite is replaced with ous. So for example, let's look at H2SO3. SO3, that's the sulfite ion, and so this is going to be called sulfurous acid. So those are the rules for naming acids. First thing you want to decide is, well, is there oxygen or is there not oxygen? If the acid doesn't contain oxygen, then you follow the rules for that. You use the prefix hydro and the suffix ic. If your acid does contain oxygen, then you need to figure out if the anion name ends in ate or in ite. If it ends in ate, then what you want to do is make sure that the root name ends in ic. And if it ends in ite, then that's replaced with ous. And there you have it. Those are the rules for naming acids. Now we can move on to our last and final discussion. This is going to be very brief. We're just going to define and discuss electrolytes for a little bit. We're going to come back and revisit this topic in Chapter 9 when we cover solutions. Electrolytes are substances that produce ions when dissolved in water. These ions, they can conduct electricity, making the solution an electrolyte. Electrolytes are important in many biological processes, including nerve and muscle function, and they help maintain proper fluid balance in the body. Now, ionic compounds, they make good electrolytes because they dissolve most readily. On the other hand, nonpolar covalent compounds are the weakest because they do not form current-carrying ions. Now, the tendency of an ionic solute to dissolve or solvate into its constituent ions in water, it can be high or low. A solute is considered a strong electrolyte if it dissociates completely into its constituent ions. So examples of strong electrolytes include certain ionic compounds like sodium chloride and potassium iodide, and some molecular compounds with highly polar covalent bonds that dissociate into ions when dissolved, like hydrochloric acid in water. A weak electrolyte, on the other hand, it ionizes or hydrolyzes incompletely in aqueous solution, and only some of the solute is dissolved into its ionic constituents. Now again, this is a topic we'll elaborate on in Chapter 9, but for now, that's it. We've completed all of our objectives for Chapter 4. I really hope this was helpful. Let me know if you have any questions or comments or concerns. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.